Okay, I want to make an announcement. Probably I should have done this earlier, but the first exam, first midterm. My plan is to give a midterm about once a month. So midterms about once a month. So the first midterm will be September 11th. So it's a Friday. And that falls about 1 month after the beginning of class. It'll be an entire, the whole time period. Of course, I haven't written it yet, and what I test you on will depend on how far we get. So in general, I'll be, letting you know closer to the exam what material to study for and what not to study for, etc. And of course, I'll be sending out more information via email about the protocol for testing and stuff like that. But I just wanted to make sure to let you know that a midterm was on our horizon. Will we have a study guide? I will kind of verbally tell you which things that you should study. I can tell you right now that it will be pretty much whatever we cover. So that's going to be chapter 1, probably sections 1.1, 1.3, 1.4, 1.5, 1.6. Probably we'll do a little bit in 1.7, stuff like that. It will not be open book, but I will give you a table with I believe, let's see, so I'll give you more information as we go on, but what I did last time and what I intend to do this time as well is to give you a front page with a certain amount of identities listed so that you don't have to memorize all of the argument forms, and you don't have to memorize all of the different equivalences that we use. But beyond what I provide you, it will not be open book or open note. Any further questions? No? Okay, in that case, I will continue. So last time, we started on nested quantifiers. And we covered the first two kind of easy kinds of quantifiers, namely for all x, for all y, p of xy. Can someone remind me how one would say this proposition? Although I kind of just said it.
Basically, for any combination of x and y, p of xy is true.
Exactly. There are multiple ways that would work. You could say for all x in the domain and for all y in the domain, they have property p of xy. Or you could say for every pair x and y, property p of xy holds. And when is this proposition false?
When we can find one counterexample.
Exactly. This is false when you can find one counterexample, which means one pair x and y such that p of xy is false, or the negation of pxy is true. Yeah, very good. Similarly, we have the following nested quantifier, and I'll ask you the same questions. How would you say this, and when is it true and when is it false?
There exists one x and y such that p x of y is true.
Yeah, I would give one quibble with your response. I would say there exists at least one, right? There could be more.
Oh yeah.
We're not saying uniqueness here, but we're saying there must exist at least one pair x and y such that p of xy holds. Yeah, exactly. And this statement is false when, well, there exists no pair such that p of xy holds, right? This statement is false whenever p of xy is never true for any x or any y. Okay, now any questions on these? This is kind of review from last time. Okay, so now we get to the slightly more interesting ones. We have the following proposition. So here's one, here's another, nested quantification. There exists x such that for all y, p of xy. So this proposition will be true when there exists some x in the domain for x such that p of x comma y prime is true for all y prime in the domain for y. So you should think of this as a kind of one size fits all. There's got to be one x which fits all of the y's such that the proposition p of xy is always true for at least one x that works for all y's. This is kind of one size fits all. And this is false when there is no single x which works for every y. False when no single x works for every y. Okay. And similarly, we have the reverse, which is for all x, there exists a y such that p of xy. And this one is quite different from the previous one. So notice that order matters. So this proposition, can someone tell me? Yes, exactly. That's going to be precisely an example that I'm about to do, Catherine. Yeah, thank you. How would we say this proposition? Yes, thank you, Val. For all x, there exists a y such that p of xy. So this is true when for each x, we can find a y. Possibly different. Y such that p of xy is true. And when is this proposition false? What would it mean if this thing were not true?
When there is no y.
So for this to be negated, there must exist an x. False when there exists an x such that no y works. No y works. Right? Does that make sense? Why? Can I explain why I used y prime for the first problem? Yeah, I mean, it's not really necessary. I just wanted to emphasize that I'm fixing one variable and then I'm letting the other variable cycle through all of its possibilities. That's all that I was trying to denote with this notation. It's not really necessary in this case. And so as Catherine mentioned, there are some nice examples. So let's discuss the truth value of the following propositions. There exists an x such that for all y, x times y is equal to 0. Can someone tell me whether this is true or false?
It's true.
Yeah, this is true. We can take, so let's say that our domains for x and y are in the real numbers. I'll just make things nice. So this is true. Just take x is equal to 0, and then 0 times anything will be 0. So this is a one-size-fits-all sort of thing. I found one single value for x such that for any possible value of y, I always get x times y is equal to 0, because 0 times y is always equal to 0. Y can be anything, and this relationship still holds. Now let's examine the reverse. For all x, there exists a y such that x times y is equal to 0. Is this true or false? Yeah, once again, this is true. For all x, there exists a y such that x times y is equal to 0. Well, one option is if x is non-zero, you can always take y to be 0, right? There's one case where we have more options, which is when x is 0, and then y can be anything, and this is satisfied. So if there, yes, I'm about to show an example where order matters. So in this case, what we're seeing is that this statement is stronger than this statement, because if there exists one x that works for all y's, then if I reverse the order of the exists and for all, then I can just take the one x that works for everything to satisfy this statement, if that makes sense. On the other hand, let's examine the following example. Exists an x such that for all y, x plus y is equal to 0. Is this statement true or false?
It's false.
Right, this is false. Also, Alex, the answer to your question is no for this reason. Exists an x for all y such that x plus y is equal to 0. Why is this false?
As y varies, you have different values for if you hold the next.
Exactly. We can
Constant,
think
right?
about counterexamples. For instance, I could let y be either 1 or 2, right? So there is something that I add to 1 that makes the sum 0, but it's different from what I add to 2 to make that sum 0, right? So this proposition is false because there's not one real number that you can add to any other real number and get 0. However, the proposition for all x, there exists a y such that x plus y is equal to 0. What's the truth value of this proposition? And Stefano, yes, you can think in terms of loops if you'd like. So this is true because for any x, there exists the negative of x such that x plus negative x is equal to 0. So notice that one of these statements is stronger than the other, but they're not equivalent. If this statement is true, then this statement is true, but this statement can be false and still have the for all statement be true. So does this help a little bit about why order matters and help us kind of understanding some of these nested propositions? Great. Any other questions before we do some translations? Cool. So the interesting part of this section, I feel, is kind of translating back and forth, especially translating English sentences into logical statements involving quantifiers. So let's get started on this kind of translation business. And also, we're gonna immediately jump to possibly having like 3 nested quantifiers and stuff like that. So it's not so bad. I think this example will help. So let's do some translation. Let's assume the proposition T of xy is equal to student x, sorry, T of xy, student x enjoys cuisine y, where the domain is that domain of x is students at UNC, and the domain of y is all cuisines. Okay, so let's try to work out what some of these logical propositions kind of work out to say. So okay, so a first thing to notice is where our variables are, like which domains our variables are in. So a first question is, what is the domain of x and what is the domain of z?
It is students at UNC.
Yes, so x and z are students at UNC, and y is?
All the cuisines.
That's right. So if we forget about the quantifiers, let's just try to think about what this proposition on the inside is saying. Anyone have a translation of just the inside? So what's the first thing say? Right, so this is saying student X is different from student Z. If I'm taking X and Z from the domain of students, there's no reason why I couldn't have selected the same student twice. So here, this is, as a first condition, it's saying, if student X is different from student Z, then it is not the case that, what? Exactly. This is saying that if student X is different from student Z, then it is not the case that both student X and student Z enjoy cuisine Y. Great. Now what happens if we add in the quantifiers? So this is saying for all students X and for all students Z, there exists a cuisine Y such that as long as you've picked actually different students, there must exist some cuisine that not both of the students enjoy. In other words, this proposition is saying for any 2 distinct students at UNC, there exists a cuisine that they don't both enjoy. Do X and Z have the same domain? Yes, here X and Z are assumed to have the same domain because really I should have specified that. To be more complete with this statement, I could have put X Z in domain students, and Y in cuisines. But as long as X and Z are playing the same role, namely they're both in the first coordinate of TXZ, where the first coordinate refers to a student and the second coordinate refers to cuisine, then you assume that X and Z are in the same domain, yes. Any other questions on this particular example? Yes, so this entire statement says, given, maybe I'll say it once more robotically and then a second more in language. So the more robotic way of saying this statement is, for all students X and for all students Y, there exists a cuisine, and for all students Z, there exists a cuisine Y such that if X and Z are distinct students, that implies that it is not the case that both student X and student Z enjoy cuisine Y. That's a kind of robotic, direct translation. If I wanted to be a little more poetic about it, what this statement says is that for any two distinct students at UNC, there exists a cuisine, Y, such that it is not the case that both X and Y enjoy cuisine, or both students X and Z enjoy cuisine Y. Does that help? Is this a true statement? I have no idea about whether this is a true statement. Probably not. Probably this is false. I mean, here's an interesting question. What are some interesting ways, like how could this proposition be false? This proposition is false when there are at least two students who enjoy every single cuisine, right? And probably there are two students who enjoy every single kind of food that can be made, I guess. I don't know. Two distinct students. Chickpeas are great. Chickpeas go into hummus. So let's do another one. There exists an X and there exists a Z such, oh well, I shouldn't say these things. I'm going to stop talking out loud and I'm just going to write it so that y'all have blank minds when you approach this translation. Here's a true proposition. Chickpeas are great. Perfect. All right, can someone give a crack at this proposition? And you can either do a part of it, like you can either start with just saying what this kind of interior proposition says, or you can try to do the whole thing in one go.
There exists a student X and a student Z for all cuisines Y, such that student X enjoys cuisine Y if and only if student Z enjoys cuisine Y, or the same cuisine.
Exactly. Now, I can pretty much guarantee that this proposition is true. Why can I guarantee that this proposition is true? Yes, exactly. In this proposition, I didn't prevent or exclude the case where X and Z are the same person. So if you take the exact same person, then of course they're going to like all the cuisines that they like, and they're going to dislike all the same cuisines that they dislike. I could make this proposition more interesting by adding a criterion like this: X is not equal to Z. And then that would be a stronger statement. If I included the X is not equal to Z and this proposition, then it would say there exist distinct students X and Z such that they enjoy precisely the same cuisines. But here, this is just saying there exists a student X and a student Z such that they enjoy precisely the same cuisines. But if X and Z are the same person, then that's obviously true. And X and Z being the same person is not excluded in this proposition. Any question here? Let's do one more. Once again, empty your minds. I suppose I don't need to say that since I'm not saying what I'm writing anymore. Okay, this one's pretty similar to the previous one. And what is this proposition?
Did you mean to do T of Y and Z, the second one?
Oh, nope, I did not. Thank you. TYZ doesn't make sense. So can someone tell me what this proposition is saying? Right. For all students X and Z, there exists a cuisine Y such that student X enjoys cuisine Y if and only if student Z enjoys cuisine Y. So this is saying that for all students, there exists a cuisine Y such that either everyone loves the cuisine or everyone hates the cuisine. But everyone is in agreement about cuisine Y. Either all students dislike cuisine Y or all students like cuisine Y. Yeah, I agree. This one's definitely false. Okay, so are there any questions about kind of this translating step or about how we parse these nested quantifiers? If Y were in front, would it be a different Y for all X and Z? So you're saying, let's consider the following proposition. Exists Y such that for all X and for all Z, T of X, Y, if and only if T of Z, Y. So this is the proposition that for all students X and for all students Z, there exists a Y such that this holds. And then this is the proposition that there exists a food such that for all students X and for all students Z, if student X enjoys Y, that's equivalent to student Z enjoying Y. Here, these look to be no, these are different propositions. Sorry, I actually made a mistake when I was talking about this one. So this proposition is there exists one single cuisine that for all students on campus, they share the same opinion of. What this statement is saying is that for any pair of students on campus, there exists a food that they share the same opinion of. So this one actually is the one that I probably said this, but this is a different proposition. So this one is, there is one food, or one cuisine, that everyone on campus agrees on. Thank you. And this proposition is for any pair of students. There exists a cuisine that they agree on. Yes, that's a very important distinction, and I think that that means that I made a mistake when I was originally talking about this one. Is this clear to y'all about the difference between these two propositions? This one says that there's one cuisine that fits all. So for one cuisine, everyone has to either agree or disagree. Whereas this one is saying for all pairs, can you find a cuisine such that they agree or disagree on it? Yeah, thank you, Stefano. That was a very good point. So this stuff can be a little tricky, and it can require some thought to parse what the different statements are saying. Any further questions here? I am going to now give a very mathy example, which should be familiar to y'all, I hope. I hope that this is not your first time seeing this. So let's translate the following statement into symbols. So use quantifiers to express the definition of a limit. So remember that a limit as x approaches a of f of x is equal to L. What this means is that for every real number, okay, hang on 1 second, there's a question. Do you not need to do the x is not equal to z for the all quantifier? If I add in the x is not equal to z, that will change this statement. So here, in both of these statements, I'm not excluding the case where x and z are the same individual, but I'm also not saying that that's the only case. So here, if I'm looking at this statement right here, I'm literally taking the set of all students and taking any pair where a pair can consist of the same student twice, but it can also consist of any other possible pair. And that's a different, and so that's what I have here. If I added in this x is not equal to z condition, then I would be excluding that, I'd be excluding that case where you take the same student twice. So it's not about whether I need or don't need, it's the fact that that leads to different propositions. Does that help? Great. So we're taking a limit. For every real number epsilon greater than 0, there exists a real number delta greater than 0, such that if such that f of x minus L is less than epsilon whenever 0 is less than x minus a is less than delta. So this is the wordy way of writing what it means for a function to have a limit at a point. Do y'all agree? Do y'all remember this definition? Is this familiar from Calc 1, Calc 2, and Calc 3? Great, I'm very happy to hear that. So let's translate this sentence into a quantified proposition. So how should we start? This is x minus a. So remember, in the definition of a limit, we have 4 things floating around. We have our variable x, we have our value a that we're approaching, we have our function f, and we have our supposed limit L. This is x minus a. So probably I would imagine that someone has to speak into their microphone for this one because it's a massive pain to write down into the chat. What's the first quantifier that I need?
For all. Universal.
Yeah, I need a for all epsilon. And I could either write a for all epsilon and then in the domain put epsilon greater than 0, or I could write for all epsilon greater than 0. Yeah, very good. Okay, so the statement says for every real number, then there exists a real number. So what's the next thing that I need?
The existential one.
Yep, there exists a delta greater than 0. Okay, now I've got my quantifiers set up. And the last thing that I have is this statement, blank whenever blank. If I have a blank whenever blank, that's going to be an implication. And does anyone remember in which direction the arrow points for a blank whenever blank? P whenever Q means Q implies P. Very good. I'm happy to see this. So what this means is I need to take this proposition, 0 less than x minus a less than delta, implies this proposition, absolute value of f of x minus L is less than epsilon. And here is the formal definition of what it means for a function to have a limit at a point A. Probably you've seen this before. I hope so. Let's do one more translation, or maybe 2 more. I don't know, how much time do we have? Not very much, okay. Indeed, indeed. I really like these ones where the domain is UNC students. So if FAB means A and B are friends, and the domain is UNC students, then what does the following proposition mean? I should put more parentheses around here. Okay. Out of all students, there exists one who has two friends that don't know each other. So it's not quite that. What this is saying is there exists a student such that for all y and for all z, if x is a friend with y and x is a friend with z and y is not equal to z, then y and z are not friends. So what this means is there exists a student such that for any two distinct friends of x, those two distinct people are not friends from each other, not friends with each other. In other words, if I try to draw the graph of friends, this is x, and then if I have any y and any z, these people are not friends. And if I have any third thing, like u, these people, none of these people are friends. No, no. So every single friend of person x like doesn't know any other friend of person x. Right, exactly. So this is one person x such that none of their friends like each other, but they all like person x. Right. So essentially x only ever hangs out with one person at a time. They never hang out with two people, because anytime that you could get two friends of x together, those two friends would hate each other. Yeah, I agree. This sounds like some pretty toxic behavior from student X. I think that this quarantine is teaching us all about some healthy and unhealthy behaviors. Great, that was a fun one. Let's do one more. So let's do the following translation. L of X and Y means X loves Y. And notice that there's some direction with these propositions. For here, f of a, b means a and b are friends with each other. But here, this is just one directional, which, you know, is how things usually work. People can be friends together and it's usually mutual, but it's very often that you can have unrequited love. Here I am talking about some philosophy here. Little did you know what you'd be educated on in this discrete math class. Let's do the following proposition. Please write in symbols the following proposition. There is a student at UNC who loves no one but themselves. And you have to make this into a logical proposition that you can then assess the truth or falsity of. Falsity isn't a word, the truth or falsehood of. I'm all out of this paper. So, can someone, yes, also toxic behavior. Can someone give me a stab at writing this in logic? So we definitely need L of XX because we know that they love themselves. And we also need the fact that if we have someone different, they don't love that different person. So definitely I want a there exists an X because I'm saying there must exist some person with this heinous behavior such that for all other students Y, right, we need two things. One, we need X to love themselves. And then what else do we need? Well, we also need the condition that they don't love anyone else. So they love themselves, and if X is equal to Y, or not equal to Y, so they love themselves, and if there's someone different, X not equal to Y implies it is not the case that X loves Y. And now I need to get all the parentheses right. Chook, chook. Here is my, and of course, please notice that there are many different ways of writing the same proposition, because once I've written this, and this is correct, then I can use any of my logical equivalences, right? I could do an implication substitution, right? I could push through the negation sign. So there are going to be many different propositions which have the same truth value, but here's one that we could start with, right? So do we agree that this encapsulates the statement that we had? There exists a student X such that for all students Y, first of all, X loves themselves, and if X is not equal to Y, then X does not love Y. Yeah, I think this is probably true too, although that's a sad thing. How much time do we have? We have time for a little more. Any questions on these translations? Oh, dang, that's some harsh words, Stefano. I choose to not believe that this is true if I restrict the domain to this class. All right. Any questions? No questions. Really, I just have more examples because I find these examples very fun. Yeah, I guess let's just do one more example. So another example, last one of the day. Let's let m of xy be X has sent Y an email, and then T of XY is X has telephoned Y. Boy, you can tell that this text is really showing its age. Can't remember the last time I called someone who wasn't like the car repair store. Okay, so let's write out the following proposition. And let's say the domain of X and Y is students in my 381 class. Let's write out the proposition. There is a student who has either emailed or called everyone else in class. How would y'all write this in terms of quantifiers? It's really hard for me not to, every time I ask you to do one of these, to say, write this in terms of facts and logic. Okay, anyways, passing that by, how would we write this? Yes, so we need an existence. There exists a student X, and then we need for all Y, and then we need either one of these two things to hold. But there's one condition that we need, because this proposition is about everyone else. We don't think that this student has called themselves or sent themselves an email, right? I now really regret saying that. You guys need to focus and bring it back here for the last remaining minute of class. Yes, I do too. But right, if we just are trying to translate precisely this statement, then we do need to include an X not equal to Y, right? Do you agree? Right. So there exists an X such that for all Y, X not being equal to Y implies m of x, y, or t of x, y. So this is saying that there exists a student such that if you take any other student in class, they have either received an email from X or they've received a call from X. Now there'd be a different statement, which might be good for you all to try to write, which is write the slightly different statement. There exists a student who has either emailed everyone in class or called everyone in class. And notice that those statements are different. In any case, here's a good collection of translations and practices and things like that. Any questions on this? If you have questions, remember I have office hours in like 20 minutes at 10:30 with the exact same Zoom link. Remember that you have a test coming up on September 11th. Well, no one said if these propositions are true or false. I'm just writing the propositions. Anyways, any other questions? If not, have a wonderful Monday, and I hope that y'all are taking care of yourselves this week.
Thank you. Have a good day.
Thank you.
Yep. Have a nice day, everyone.
Thank you.
Thank you.
So long. Dawson and Alyssa, do you two have any questions? If not, I'm probably going to just end the call, and you can come to office hours if you have questions. No problem.